Dr. Dubey received her PhD in electrical and computer engineering from the University of Texas at Austin in December 2015. She is currently an assistant professor in the School of Electrical and Computer Science at Washington State University, Pullman, USA. Her research focus is on the model-based and data-driven methods for the decision support in the large-scale electrical power distribution system for improving the efficiency, operational flexibility, and resilience in response to the massive integration of distributed energy resources and extreme weather events. The thrust of her research area is embedded in the developing novel algorithms for the cyber-physical infrastructures via the use of optimization, stochastic modeling, and autonomous control. She is a recipient of National Science Foundation NSF Career Award. She is also serves as associate editor for the IEEE Transition Power System, IEEE Power Engineering Letters, IEEE Access. She is currently secretary of IEEE PS Distribution System Analysis Subcommittee and IEEE PS University Education Subcommittee, and serve as PS Chapter Chair for the IEEE Policy Section. Ma'am, it's a pleasure that you have accepted our invitation and spared some time from your busy schedule to enlighten us by your knowledgeable words. So on the behalf of whole Para 21 team, I welcome you. Now I request Dr. Dubey to continue her talk. Over to you, ma'am.
Thank you, Gaurav. Thank you for the kind introduction and thank you for the invitation. So I'll start screen sharing. Let me know if you can see it.
Yes, it's visible, ma'am.
Okay, awesome. All right. So hello, everyone. Good morning to all of you. I'm glad to be invited in this for the talk today. My presentation today is going to be about distributed coordination of network microgrid for grid services. So I'll jump right into it. So the main motivation for microgrids and this topic that I'm going to discuss today is basically the changing nature and requirements of our power grid. So you know that the power grid is getting more and more decarbonized as well as it getting more distributed. So we are actually heading towards a decarbonized and a distributed future. We are seeing large penetration of distributed photovoltaic systems, and this is happening worldwide. We are also seeing new types of load, which is again happening worldwide, where we are seeing plug-in hybrid electric vehicles or electric vehicles that are being integrated. New kind of loads are emerging, for example, data centers. We are also seeing that power electronics-based devices are becoming ubiquitous, and then we also have different more and more active nodes in the distribution system that are being integrated. So the main this is basically the nature of the grid that is changing. Our requirements from the grid are also changing. In fact, we want more continuous power supply, and I'll talk briefly about that. But the main point is that there is a need for this distributed coordination of all these controllable devices for having higher flexibility among distributed energy resources. So as I said, we also have increasing requirements from the grid as well. We are seeing a dramatic increase in extreme weather events. And I have data only from US, apologize for that, but in general, we are seeing that extreme weather events throughout the world are increasing. They're causing huge amount of damage to the power grid, specifically at the distribution level, and they're costing a lot. In fact, even the frequency and the and the cost of these outages are increasing significantly year on year. Okay, so this basically motivates the use case for microgrids, and that's why I had that motivation. Microgrids are basically, one way of coordinating these all distributed energy resources over through distributed coordination, right? So there are these advantages to having these microgrids in the system, where you can have higher resiliency because networks of microgrid might be able to self-assemble, and they might create, if when there is a loss of bulk power supply, they might also offer scalability for large number of distributed devices, which can be integrated through a layered coordination structure. And I'll talk more about that. They also add operational flexibility. So for example, you don't have to have a fully centralized coordination of the grid. There are more edge coordination available, and that help you integrate more and more distributed devices and add more operational flexibility to the network. which also adds to the resiliency. And then there is also operational efficiency, and then multiple more operational options because you have more decentralized or distributed control centers located with the help of these microgrids. One example of using these microgrids for the kind of services that we just talked about is basically, for example, if you think about it, let's say there is an extreme weather event, most of the grid is outage. One of the major application of microgrids is to be able to provide continuous supply for some of the critical assets, right? So for example, if you have planned the microgrid properly, it's possible that you can energize part of this island, which might contain, let's say, hospitals or some other critical loads, and then you can still supply them, right? So this and other related reasons have led to increase in the deployment of microgrids over years. And this is basically showing a trend that how the microgrid deployment is going to increase in the coming decade. And the trend is basically extrapolated based on several factors, and it's coming from this resource that is given here. The main point is that we are going to see a more and more proliferation of these microgrids, and I'm calling them resilient because I want to connect their use case to the resiliency of the power grid. So basically, the next step for this problem is also to look into microgrids as a solution for resiliency, and that's the topic of today's discussion. That how a network of these microgrids can be used to provide different kind of grid services. So for example, if you think about this network, let's say that you have created a bunch of microgrids here in the system, and these microgrids, let's say, are maybe they are privately owned, maybe they are utility owned. The main point is that if all these resources can be coordinated together, or all these microgrids can be coordinated together in a network of microgrids, and they can provide different kinds of services. That's basically what we are looking into in this project, that how can we enable that? How can we enable a network of microgrid to be able to provide different kinds of grid services for both at the distribution level as well as the bulk grid level. So for example, at the distribution level, you can think of services such as restoration, intentional islanding, critical load supply, and bottom-up restoration process, where you can build a network bit by bit as you connect these islands together. Then at the bulk grid level also, there has been use cases that are emerging. For example, if you have a major contingency at the bulk grid, and you have distribution connected, and you have a bunch of distributed energy resources which can feed the power back, or which can provide different kinds of services such as frequency and voltage regulation, then these network of microgrids can be called upon to provide those services as well. Likewise, you can also think about black start capability, which is basically if you can use the distribution connected assets to restore the power supply one bit at a time at the bulk grid. Of course, these applications will only be feasible if you have a very high penetration of microgrids as well as distributed generation resources in the network itself. So let's start the conversation assuming that that is the case. Then we think about that what are the different modes of operation that these microgrids can be operated, and basically how we can extract different services, and what are the real challenges here, and how do we then solve it. So for example, we can imagine 4 modes of operation for these networks of microgrid. One is basically a normal, where this microgrid is connected to the bulk power system, and the main objective is just to satisfy the economic objective for the microgrid itself and the loads which are being supplied by it. The other 3 modes are really interesting. They are about resiliency, and mode 2 could be, for example, a normal operation where microgrid is connected, it's still grid connected, and it's operating to support bulk power systems. So for example, for frequency regulation or for voltage control. Mode 3 could be more of a case when you have an extreme event, and in that case, your distribution network is not connected, and then the microgrids can be used to support critical load and end use load, and you can even imagine forming a network of these microgrids or flexible boundary islands to be able to supply larger and larger part of the load. And mode 4 is basically, it can mostly be activated only once you have a very high penetration of these renewable or DER connected microgrids at the distribution level. But you can think about it that they can provide new services, such as they can restore the or black start capabilities for the network itself once there has been an outage. So both at the distribution as well as maybe even at the bulk grid level. So let's assume that these are the services that we want to extract from a network of microgrid. Then the questions are really what are the operational challenges that we have here when we want to manage a bunch of these network microgrid. And the main point here is what we are lacking is basically how we come up with flexible operating strategies so that we can integrate these centralized and decentralized control system. So, a typical operation for the power grid is basically centralized. Even if we think about the distribution system has an operation center, it's mostly a central control center, right? But when you have a bunch of these microgrids, then we are talking about a bunch of decentralized control centers which are distributed, in a network. For example, this microgrid can have its own microgrid controller. This can have its own, and it should have its own microgrid controller. The point is that how do we coordinate these operations, these decentralized and centralized systems together? So that's one challenge. Then other challenge is also how do we engage the utility and non-utility assets? And that brings up new challenges. For example, the utility and non-utility assets can have different objective functions. And how do we work with those kind of scenarios then? Also, there are challenges when we are looking into these distributed coordination strategies or basically decentralized, operations. We are looking into communication related challenges. So how do we make these control strategy to be robust to communication outages, or what really are the challenges when we think about, these kind of operational paradigms? So this is in this talk today, I'm going to talk about some of the recent work that we have been doing in this problem space and what we have accomplished so far, what our findings have been, and where we are heading in this project as well. So there are three key things I want to talk about. One is, of course, how do we do the distributed coordination? So I'll introduce a distributed optimization algorithm and talk about how does it help in making these distributed decisions and what really are the unique challenges there and that we were able to mitigate through the approach that we proposed. And then we'll talk about how we can use this network microgrid to coordinate the decision in distributed manner for one specific grid service. And that grid service in this case is basically restoration of the power supply once you have a major outage. And then I'll also talk about some of the work that we did with the co-simulation with the communication network and see how the communication system ends up affecting our network, ends up affecting our operational strategies and what are the challenges that we should be aware of when we are building these kind of new operational strategies. So let's start with the distributed coordination of network microgrid and talk about the algorithm. So briefly, what centralized versus distributed coordination, what are the challenges and what really are the advantages of using distributed coordination? So when you think about a centralized coordination, really you're thinking about a central control center that gathers all the information and decides upon the best decision, right? And that's really most of the our grid is operated in this fashion. So you have some of the challenges that have been listed, which will become more and more grave as we have more and more resources, have to do with extensive communication requirement. Every device has to communicate with the central control center, and central control center has to communicate with every device. Likewise, they are prone to single point failure. So if your communication fails at the central location, then you really cannot do anything with the network, and all the controls, basically all the control resorts to local control mode, and anything you are doing from the central control is gone. There are challenges to managing non-utility owned resources, because if these resources are non-utility owned, they are not really are required to make their they cannot be basically controlled by a central control center because they don't have any jurisdiction on this non-utility owned resource. And then there definitely are computational complexities. So if we are going to operate everything from the centralized operational paradigm, depending upon what kind of problem you end up solving, you might see a huge computational complexity that might not be able to, that might not enable you to solve the problem within the time domain that you want to. So that basically, brings back these distributed coordination paradigms. These are, few of the reasons. Of course, when we get to a microgrid paradigm, the system is already distributed, right? And we have to go to the distributed paradigm automatically. But the main rationale behind, distributed coordination have to do with reduction in the communication overhead. You can manage the ownership boundaries better. There is added resiliency because single point failure is avoided, even if one of the control centers is out or control agents is out. The rest of them can still talk and coordinate the decision among themselves. And you also have reduced the computational complexity because you are now solving smaller problems, which are for given distributed area instead of the whole joint problem for the entire network. So these are some of the advantages which are in general there for distributed coordination or distributed optimization methods that are being used for power systems operational setting. They are used not just for network microgrid, but in general for the network, it's just network operation itself. But we are going to see the application for the network microgrid. So briefly, I want to talk about the distributed optimization. The main idea here is that you have a decomposable problem structure. So, a typical, if you are looking into distributed coordination and you want to, let's say, optimize certain functions, certain objective function that you want to work with, what you are really looking into is some sort of optimal power flow problem. Now, if this optimal power flow problem can be decomposed and it has a decomposable structure, then you can formulate a distributed problem out of it. So this is just a visual description on how and what you can imagine. Let's say if we assume a radial distribution system, the methods work even for non-radial systems, of course, but this is easier to show the description. So let's say that we have one network, we have decomposed this into 3 areas. What we are looking into is decomposable problems where we have created certain copy of the variables, or even not just the copy of the variable, but exchanging just the boundary information, so that while we are solving the smaller network or smaller problem, we are still able to converge on these boundary variables, which are basically carrying the information of one area to the other area. The whole idea is that in a distributed setup, you are able to decompose the centralized problem into several smaller distributed problems. You solve those smaller distributed problems with a partial visibility of just the boundary bus, and then you try to converge on the boundary bus or get the consensus on the boundary bus, so that you are able to get the network level solution which a central agent will get. The advantages are that you are basically solving smaller problems. And of course, you can use distributed controllers to work with this problem. The added problem is that you have to iterate over the boundary so that you can converge. So that brings back this point that we want distributed optimization methods which require fewer number of iteration among these agents. So some of the state-of-the-art methods, for example, that use distributed optimization techniques take more than hundreds rounds of communication among these agents to be able to converge on the boundary variable information that we want to converge on. Likewise, some real-time control algorithm also take a very long time to get a consensus. Unless you get the consensus, you are really not solving the network level problem. You are solving only a partial problem, which is partially visible to only local, also distributed agents, right? So the main point really was that we wanted algorithms which can converge faster, and by converging, I mean that can converge faster on the boundary variable, so that they have to exchange fewer number of information among the distributed agents. Why we want to do that is because, of course, the communication bandwidth and the communication latency has to be taken into consideration when we are looking into an actual power grid. So we have to devise solutions which are, deployable and which are, more robust to these communication delays that you might be seeing, or the communication related challenges that you might be seeing. The whole idea is that we want to design some algorithms that basically converge faster. And we were able to develop, we of course tested these methods for existing methods for some other networks as well, but for a strictly radial system, which is radially operated, not designed radially, but radially operated, we were able to figure out an approach that can help us solve the problem in a much faster way. So you have to take very few number of iterations to converge on the boundary if you just exchange the variables properly. And really the main idea was that if you have a radial network, then if you just exchange the variables properly, which means that if you exchange the power flow from the downstream and the voltage from the upstream, and you just make this distinction between the variables that you are exchanging among upstream and downstream areas, then this method converges very fast for any kind for any kind of decomposable optimization problem over a radial distribution network. So this slide is explaining the algorithm. I don't want to go into detail because of course, a time constraint, but the main idea is really, as you would imagine, it's an iterative approach. What happens is that every node, if you imagine, is a control center. It solves its local problem based on the partial observability from the neighbors. So for example, from its downstream neighbors, it only knows the P flow and Q flow, and from its upstream neighbor, it only knows the voltage, and it solves its local problem. And once it has solved its local problem, or it sends out the information. So it sends out the voltage to all its downstream nodes and sends out the power flow to its upstream node. And this process is repeated till this every node is able to converge on the boundary variable. And that's how you can solve a centralized optimization problem using distributed coordination, and still it doesn't take a very long number of iterations to converge, and it converges faster. So this was crucial for us because we wanted to develop some algorithm for network microgrid to work with for some more complex problems. And we were able to scale it for this simple problem and converge it, and compare it as well with state-of-the-art ADMM, which is the distributed optimization algorithm for some test system, couple of test system actually. Test system 1 is a smaller one, and test system 3 and 4 are the larger test system. This is a test feeder, which is IEEE 8500 node test system, which is a distribution test feeder. It's a decent sized test feeder. We have only worked at least in this simulation, we have worked with a single phase equivalent of these models, but they also work with a 3-phase equivalent. And you can see that the proposed approach converges very fast. At least it takes very few number of macro iterations compared to the state-of-the-art, method. The main point that we want to highlight is really not that we are great than state-of-the-art method. The main point we want to highlight here is that the structure of the problem, if you understand it carefully, it can help you get better algorithm for working with the problem. So, for example, the method that we propose does not work if your system is not radial. But if your system is radially operated, then it works very, very well. So that's the whole point. That if you can come up with methods that can leverage the structure of the problem itself, you can get better performance and much better algorithm that just work for that particular setup. Now, so okay, fine. So we have a distributed algorithm for solving these problems, but that doesn't solve the entire problem, right? Because what we are looking into is how do we are looking into how we actually do the distributed coordination among these agents for different kinds of application. And that requires even further understanding of what is needed at the level of these microgrid agents to be able to do this distributed coordination in a successful manner. And these are some of the things that we identified. For example, one important point is the careful selection of the control hierarchy. So you have to, of course, figure out this hierarchy in a proper way, because there are reliability consideration for the grid, right? So you need to make sure that while these control decisions are being taken place, someone is still responsible for the reliable operation of the power grid. So you cannot just make everything distributed and then just forget about that. Then once you get to this kind of model, you also have to be cognizant about what model and what measurement information you have to share among these distributed agents, so that you can actually design the modules for it that work in a consistent manner across the network, right? And for different kinds of application. You also have to know about what kind of visibility you are assuming for these problems from these network agents, right? And also understand the compute complexities, conversions for different kind of problem, and realize the fact that you might not be able to reach the same optima for different kind of problem setup. But let's talk a bit more about that. How do we make this, distributed coordination happen in a reliable manner in a grid setup? And that basically motivates the point of this layered architecture. What does this layered architecture says is that while you can have a bunch of distributed agents which are solving for their own areas, you still have to coordinate the decision, or at least coordinate the actions with the centralized agent, which should know what's going on in the network. It might be required to validate it. It might be required to solve a part of the problem. There are different kind of architecture that can exist depending upon what kind of application you are solving for. And I'll show you one such application. The main point is that this layered coordination structure enables us to combine, these advanced strategies or control strategies with the legacy or with the existing strategies that exist in the power systems operations. And there is a reason for the synergy to exist, because that really help us maintain and integrate these new devices and new type of operational strategies in a more reliable manner. So, for example, this is a layered architecture that we are using for developing different kind of applications, specifically for network microgrid setting. You can imagine that there are a bunch of distributed agents which are responsible for their individual microgrid. they can talk to each other and they can coordinate in a peer-to-peer manner, and they can decide what they should be doing while they can actually optimize for the entire network level objective. And then that's basically layer 2. The layer 1 is the ADMS, which is a distribution management system layer that is responsible for overseeing the entire network and the decisions that are happening by these distributed agents. They might have the ability to influence some of the decisions. They might not have the ability to influence all the decisions. Likewise, there are a bunch of these local control agents which are basically responsible for executing the decision that they are getting from these higher level agent, right? So within this architecture, I'm going to show you one application. And this application, as I discussed, is about distribution restoration. So restoration is a very classical application at the distribution level where you have out of service area and you want to close some tie switches or sectionalizing switches so that you can supply that out of service area with the help of other feeders or any other distributed energy resource that you might have. With that application in mind, let's talk about what are the required measurement model and what are the methods available out there. There are different kinds of method, but the main point is that you want to, if you are making this decision in a centralized manner, you need to know what is the current status of the distribution feeder, where the fault has happened, what fault has been isolated already, and you need to know what other devices are out there. And basically what you can do is solve an optimization problem that tells you that maximize the load restored for this particular situation given these number of resources. And you solve that problem, you figure out what should be the status of the switches or any other load control devices or DG devices in the network and figure out the best restoration plan. Now, why do we want to distribute this application? One of the reasons, of course, is that, as I discussed before, network microgrids can be used for providing the resiliency service, and one of the resiliency service is restoration. If you're using network microgrid to provide this service, these microgrids have their own control center, so you need to coordinate their decision with the decision of the central ADMS to get a restoration plan that incorporates the services offered by these network microgrids. Okay, so that's why you need to distribute it. But when you are going to distribute the problem, you have to realize that for this particular application, there are two classes of controllable agents. One is basically the feeder level agents, which are owned and controlled by the central ADMS. These are sectionalizing switches, tie switches, utility owned DGs and DERs. There are also other class of controllable agents which are controlled by microgrids. So these are load or DGs within the microgrids, which are or the switches within the microgrids, which are only controlled by the microgrids. So if you're going to distribute this problem, you need to be distributing it in a manner that that who is responsible for what kind of operation, and basically based on that you end up coming up with an algorithm that incorporates that particular operational functionality. So that's where the layered coordination structure gets useful. And then we'll talk about how do we develop algorithm within this layered coordination structure. So you still have a centralized agent. As we said, that this centralized agent is responsible for overseeing the entire distribution network and making sure that the system still remains reliable after you have restored the network. There is no operational security violation. There are no other, odd kind of configurations that are coming up. This centralized agent is responsible for finding an operational topology, which is the switch statuses. Then you have a bunch of these distributed agents, which are basically, you can imagine these to be microgrid controllers. And these microgrid controllers can talk to each other and they can come up with a configuration for their own devices so that they are still meeting the objective of the restoration, which is maximizing the load restored, right? And then that's level 2 of the operation. And this level 2 of the operation is basically peer-to-peer coordination or purely distributed coordination. So using the algorithm that we discussed before, right? And level 3 is basically the local control, where they execute the decision that you have already got from the level 2. And these are basically the local devices which are within each and every microgrid area. So these could be local DGs, local load, local switches within the microgrids, which are executing now the decision that the microgrid controller is sending after converging upon a solution by talking to everyone other of the microgrids, right? And we're not talking to everyone, we are just talking peer-to-peer. So the closest neighbor is the one that you're talking to. So with that context, let's see how we can solve this problem. So now once we have this architecture, we want to fit an algorithm. And that algorithm's purpose is to find out a restored topology that uses this network microgrid to maximize the load restored. So this level 1 of the problem is basically solved at the ADMS level. Let's imagine certain operational setup. So let's say these are two feeders in the system. You have a bunch of tie switches and sectionalizing switches here. So these are the sectionalizing switches that you see here. These are the tie switches. Let's say that there are 4 areas here, and each of these areas correspond to a microgrid. Okay, so you do have a microgrid here, and these 4 microgrids. They have to coordinate together to basically come up with a restoration plan. Maybe outage has already happened, and maybe somewhere an outage can happen, and then I can show you. But the main point is that the feeder, these switches that you see here, this one, and maybe this one, and these tie switches are owned by ADMS. They are not owned by any of these microgrids. So these switches has to be decided by the ADMS. So what we do is that we basically get a switch level aggregated model where we say that everything inside this area is condensed into one node where you have just equivalent load and generation. And you solve this reduced network model to get basically a topology that maximizes the load. And that is basically stage 1 of the problem. And in the stage 2 of the problem, individual microgrids actually, which have full detailed model, they solve their own areas, coordinate the decision to find out the final load that they want to curtail or the DG they want to activate so that they can maximize the load restored. So this is how the 2 stages work, as I discussed. So stage 1, if you have an outage, let's say here, the purpose of stage 1 is to just find a restored topology. And stage 2, once it knows the restored topology, those particular microgrids which are active, so for example, in this case, A1, A2, and A3, they talk to each other and decide what load they have to curtail so that they can maximize the load restored while still satisfying the feeder constraint. So for example, in this case, this microgrid ends up curtailing load at node 4, this microgrid ends up curtailing load at node 13, and likewise here at node 20, right? So that's one possible solution. And this has to be done because, it's quite possible that after the restoration, some of the operational constraints are violated. So for example, some of the line limits, thermal limits might be violated, or the voltage constraints might be violated, right? And you don't want to do that. So to not be able to do that, you might have to curtail some of the load. So that's basically what stage 2 is doing. What I'm trying to show you here is that how this network microgrid can be used to basically restore the network while coordinating the decision with the centralized agent, which is responsible for the feeder level switches. And this is where this, the combination of the layered coordination along with the distributed optimization becomes important. So if we get to the algorithm in stage 1, as I said, what we are really trying to solve is that once an outage happens, what is the good topology to work with? What is the good topology means what switches I should on and off so that I can still get a good topology where I have a maximum number of loads to be restored. And this is a algorithm for that. This algorithm is basically looking into the reduced network and making sure that the power constraints are satisfied. It's a mixed integer linear program that you can solve through any off-the-shelf solver. The main point is that it tries to maximize the load supply using that reduced network model. So it's solving a small problem. And once it obtains the topology, then what happens is that you go to stage 2, where stage 2 basically has these 3 areas are solving individual local problems, coordinating with each other to come up with a plan that basically maximizes the overall load restored in the system. So these 2 examples are basically showing you one normal case where you have a small area to be outaged, and here it's an extreme case where you are seeing main feeder to be outaged and how can you form islands to work with the network. So both cases can be handled. And this again goes to basically the algorithm for this one, iterates over 2 stages. So this is basically one mixed integer linear program that individual area solves. And what they are really solving is they are maximizing the load within their areas while satisfying all the constraints within their areas. And they are exchanging the boundary solution as we mentioned before, right? This is called micro iteration, which is solved by each of the areas. And then you go to macro iteration, where what happens is that these areas exchange the information and they do that till they converge on the solution. So you do multiple steps of micro and macro iteration, and you keep on going until you converge on the boundary. And that again goes back to the distributed algorithm that we talked about. And final solution is basically what loads to curtail in this area and what DGs to activate so that you can still, restore the maximum load. So this is just, summarizing what we just talked about, and I'm going to skip it, but I'm going to talk a little bit more about here that how it all fits together. So you can imagine, let's say there's this notional feeder, which is like a 25 bus node system. And as I discussed before, let's assume that these 4 areas are your microgrids and you want to network them so that you can maximize the load restore, right? So that's what we are doing. We're networking these microgrids so that we can meet a resiliency goal or meet a restoration objective. An outage happens. This is a simple outage where this area gets outage. You open this sectionalizing switch so that you can isolate the outage here. And now you have rest of the feeder, which probably is still supplied, but there might be some operational constraint violation that might be happening, right? So you might have to come up with an alternate configuration for this particular, feeder so that you can still maximize the load restored that might be happening in the network. And what you can then do is talk among these areas to make sure that you can still satisfy the constraints which are local to these areas while making sure that your load restoration is still maximized. So this is a stage 1 where you get the topology. And then this is a stage 2 where you're doing multiple macro iteration to get to a converged solution. And I'm going to briefly talk about some of the results here. So for example, in this case, you can see that, and what I'm going to do is I'm going to compare this result with a purely centralized approach where you have all the information. So for this particular case, you can see that if both centralized and distributed optimization give you almost close result, which is how much power they can supply from the substation after an outage. And the time taken is almost comparable for both the problems. Now, we also tested it for a larger feeder where we have, these 4 feeder test system. And every of these feeder is basically combined of these 20 areas. You can imagine these 20 areas to be networks of microgrids, right? And they are talking to each other, coordinating to make a decision. And we tested this approach for, different types of outages. So here we tested it for different feeder capacities. So as you constrain the feeder capacity, of course, you will see how the outage plan changes for normal kind of faults. And you can see the centralized model and the distributed model gives almost the same result. So here we're just testing how efficient our distributed model is. It's not exactly the same results because you're not getting to the exact optimal solution because you're still solving a mixed integer linear program, which is non-convex, but you're still getting close enough solution, which is decent and can be used to coordinate different control agents here. Likewise, even for an outage case where you have to form an island, so for example, there's a major outage and you have to form a bunch of islands to resupply some critical loads, both distributed and centralized models are able to get to the similar solutions and within the reasonable time. So that's just showcasing one application, how you can work with using this network microgrids to provide a restoration objective. Now, some thoughts here are basically, you can use this kind of approach, level 1, level 2, to achieve the restoration objective, which might be needed if you have, different kind of decisions making agents which are responsible for different types of, devices. There are other methods of decomposing the problem as well. You don't have to level 1, level 2. In fact, all the agents, including the ADMS agent, could be at the same level, and they might only just be talking peer to peer, and you might still want to solve the problem. So there are different ways of decomposing the problem. It also depends upon how you decompose the problem and what you solve depends upon several factors, and it needs a lot more careful observation and consideration depending upon what problem you are solving, what objectives you are meeting, what kind of operational flexibility you have, and what is a more scalable approach. And further, research is needed really to answer all those questions. So with that, I'm going to briefly now pivot to this point that I mentioned before. In last 10 minutes, I'm going to talk about what is the impact of communication systems and in these distributed coordination approaches, what we have done so far, and what do we think could be the next step in this work, right? So as I discussed, this is what our problem is. We have a distribution network. We have a bunch of microgrids, which we want to network through communication to meet certain objectives, right? To meet certain network level objective. In previous case, for example, it was to restore the maximum number of loads. Now, to solve this problem, when you are trying to work with, for any kind of grid service, you need to be able to communicate among these microgrids. That's first thing. If the communication is outage, then this coordination is not possible. But even if the communication is there, you still have certain limitation as to what kind of communication network model you have, what kind of bandwidth you have, what kind of latency you have, so that you can make sure that the decision that you want to take is done in a timely manner. Now, for restoration, probably it doesn't matter that much because that's after the math of an event, right? But for example, for some other application, let's say that you want to provide an active power support or frequency regulation support from these agents, right? And they have to meet a power level target, in that case, it's very important that you are making these, conversations or communication in a timely manner if you want to respond to, let's say, a certain event that is happening at the bulk grid level, right? So then it becomes more and more crucial to make these communication faster so that you can actually provide the grid service that you wanted to provide. So that brought this question that we need to evaluate these distributed algorithms from the perspective of the communication network model as well, and that required us to do the co-simulation of power communication and control layer to figure out how these control strategies that we are developing are affected by the communication models, right? Or are affected by different types of communication networks or communication network parameters. So what we did was basically we developed a co-simulation platform. This is to do the study. So we developed a co-simulation platform which did this power communication and controls co-simulation. This is a notional figure of this, co-simulation platform. We are working at the distribution level. The power simulation, which is the distribution system simulation, is done on the distribution solver here, which is called GridLab-D. Then the communication system is simulated in NS3, which is a network simulator for the communication network. All the control agents that we are working with, for example, these local control agents which are controlling individual devices, and also these microgrid control agents which are controlling the microgrid itself, right? They are coded in Python, and we are using Helix platform, which is a PNL developed platform, to coordinate all these decisions and to work with, all these, co-simulation setup. And the reason for doing this, of course, is so that we can study this. So here is an example. Let's say that you have two microgrids. Every microgrid has a microgrid agent. This microgrid agent is coded in Python. So it executes, reads the information and executes the control decisions that we want to work with. Then you have a communication layer. This communication layer is basically used for communication among microgrid agents and also communication with the device agent. This device agent is basically controlling individual devices within each microgrid. And then you have a physical layer where every of these interaction is going on. So you have a cyber layer, you have a physical layer, you have a control layer, and all of this is co-simulated in Helix. So this slide is showing you the physical layer. So for example, let's say an IEEE 123 bus system. This is simulated in GridLab-D. You have, let's say that you decompose the system into 4 areas, and these areas are basically the microgrids. Assume that, and they have their own microgrid controller, and every of these devices that you see here, any active device that you have, they have on their device controller. So that's what we are coding here or modeling here. The physical layer models the full detailed model of the power grid. And the communication layer basically modeled any communication that is taking place among the microgrid controller and the individual devices, or the microgrid controller and the other microgrids that are in the network, right? So for example, in this case, we are modeling a peer-to-peer setting where every microgrid is able to talk to its own devices. And every microgrid is able to talk to its neighboring microgrids, whichever it is directly, connected to in the physical grid. So we can develop different types of this communication architecture, and that's the flexibility that we were looking for, so that we can evaluate the performance of these algorithms as your communication architecture changes. So this is how the Helix OSIM platform really works. So you can imagine, we want to talk to microgrid 1 talks to want to relay certain information to microgrid 2. The microgrid message gets initiated. Then you have a Helix broker, which basically reads it, and it transmits it to the NS3. NS3 receives the message, and the message remains in the simulated network. At the next time step, it basically sends the message out to the microgrid 2. Microgrid does its computation, does the data processing. It might be solving some optimization problem. It might be just reading the information and solving some real-time control problem. It might be doing different things. After it has done that, it basically sends the reply back to the Helix broker, which goes to the NS3 simulator, which goes through the NS3 simulator for discrete time step, goes back to the Helix endpoint, and then is sent back to the microgrid controller 1. So this receives the information now. So this way you are able to simulate the effect of the communication when this microgrid 1 is trying to talk to microgrid 2 for any kind of control application. So that's what this enables us. And in this NS3 simulator, we can simulate different type of topologies of this microgrid. We can also simulate different types of communication latencies, bandwidth issues, packet drops, all kinds of problems. And that is what we can use to do the evaluation of the algorithm that we are working for the distributed coordination. So there's some example, just very preliminary result for us to work with. We try to, benchmark the centralized OPF with the distributed OPF in this setting for different types of delays in the network and for different, actually this is only for different delays. So you can see that both of centralized and distributed is going to be, is able to get the same solution for this particular case. The reason is because we are basically able to take very few number of macro iteration, and we are still solving a quasi-static problem, right? Because if in this one we were solving a loss minimization problem. So if you're solving a loss minimization problem, that really is a quasi-static problem. And if you're not taking a very long number of macro iteration, which is the communication round among microgrids, and you are still able to solve the problem within 8 to 10 or 4 to a single digit or a double digit macro iterations, then you are not going to get a lot of delay, a lot of difference in the optimal solutions. And that's what we observed for this one. Then what we did was we tried to study different types of microgrid communication topology and see its effect. So for example, this is the simplest topology where each of the microgrid controller can talk to its own device, and it can talk to the neighboring microgrid it is connected to physically in the network. Other case was more extreme, where you are following all ring topology, where every device can talk to every other device through this ring topology. So for example, if the C1 wants to talk to, let's say, or C4 wants to talk to, let's say, 78, then it has to go through this entire network to actually be able to talk to it. So that was the delay that is added. The other one is the star topology, where you have basically one central location, and then it's dispatching the information to every other node. And the fourth one is basically, again, same as case one, but in this case, you are really looking into non-physical network kind of topology. So actually, in the physical network, C3 is not directly connected to C4, but you are basically making it happen here in the communication topology. To test that, how does that affect? So we did some simulation. We are still working with the quasi-static simulation, so there were not a lot of difference in terms of what we actually end up getting the converged result. But there were differences in terms of how many iterations it takes us to converge, or how much time it really takes us to converge for every case. So for example, in the ring case that you saw, it takes the longest time to converge because it has the longest path to follow to reach and communicate any decision, right? And likewise, you can see that this minute 2 and minute 1 and 2 are basically 2 steps of the operation. And you can see in either of the cases, the case 2 or the ring topology is taking the longest. Likewise, the star topology also takes a very long time because you have just one central location through which every information has to be relayed. There was not a lot of noticeable difference in terms of getting the optimal solution. So because we can solve the distributed problem very fast, we were still able to get the optimal solution that we wanted, but there were, of course, differences in the micro steps that it takes to get to those solutions. So the key takeaway is basically that we have evaluated these algorithms for certain application which are more traditional. Yes.
Voice
Sorry,
was
say that,
breaking in between.
say that again. Hello.
It's a little bit breaking in between.
So Gaurav, your voice is breaking.
Yeah, now it's fine. Now it's fine.
Okay. Sorry about that. So okay, so let me continue. So the key takeaways basically was that we did evaluate some of these algorithms with cyber physical core simulation system, which was important for us to understand how these distributed algorithms perform when you have different types of communication topologies, communication related communication bandwidth, or even delays. We need to do more extensive simulations for sure. We also need to do more extensive evaluation of our restoration methods that I have previously proposed. What we have tested so far have been a simpler problems such as loss minimization and more continuous and quasi-static problem. We also, the future work also entails, of course, as I said, algorithm benchmarking different communication strategies and also different solvers for solving this optimization problem, and how does that pan out, and looking into even more larger system with more number of microgrids that are being coordinated. So some other ongoing and future work, and this is pretty much my last slide, and I want to open up for question and answer from here. But the main point I also wanted to draw your attention to is that there are different other applications that we should think about when we look into these network microgrid. And I talked about grid services. One of the grid service I discussed was basically restoration in this problem, but there are other grid services which are becoming, or which might have a lot of benefit from the distribution side to provide. So for example, if you have battery storage unit, or if you have a lot of DGs in the system, and power grid or bulk grid sees some sort of frequency issue or some sort of voltage related event, then you can coordinate these resources within these microgrids and these network microgrids together to be able to provide that active and reactive power support as well. This is one other application that we are looking into, and to truly evaluate and develop an algorithm for this application, we also need a model for the transmission or the bulk grid, so that we can emulate the cases on the bulk grid side. For example, let's say there is a fault here, so we can emulate the contingency on the bulk grid side and see how the distributed resources are able to actually mitigate that contingency or not. And that will also help us evaluate what penetration of these resources we will need to be able to do anything about at the bulk grid level service. So this is something that we are also looking into. This even makes it more crucial for us to evaluate the communication issues, right? Because these are more dynamic event, and these network microgrid has to converge on a solution much faster to be able to respond to this event in a timely manner. So we will be doing more and more work with the communication model and looking into how our distributed algorithms perform when we stress the system, and can it actually lead to some type of instability instead of actually helping the system. So that's some of the ongoing work that we'll be doing. And with that, I would like to finally acknowledge the funding and support from Department of Energy and Pacific Northwest National Lab. I also want to acknowledge my students who have worked tirelessly on this project, and it's basically their work. These are some of the references which are about the work that I have discussed before. And this is my research group, and these are gratefully acknowledged collaboration of my students, and also the sponsorship from different organizations that help us do the work that we do. And with that, thank you everyone for listening. I'm sorry if there were glitches with the communication, but I'm open for questions, and it was a pleasure presenting the work. Thank you.
Thank you, ma'am. Thank you for this wonderful presentation. I hope most of us have enjoyed this presentation. Now, ma'am, we already have some questions that were sent to us during the presentation. So first question is, that was sent to us in this chat box. So the first question, what will be the case in case of mesh type? I'm not sure what he's trying to ask. Anyway, so the next question is, what is the communication rate for solving distributed optimization?
Gaurav, I do understand the question. I can go ahead with that one.
Okay, ma'am.
Sure. So yeah, great question. So I think the question is basically, this method has been working. As I said, this distributed optimization is for the radial network, right? Now, distributed optimization doesn't have to be for radial network. What distributed optimization really says is that it's basically is this point, right? So if you have a problem, which is an optimization problem, it can be decomposed. You can always decompose an optimization problem into multiple areas, and you can use iterative algorithms to really solve this distributed optimization problem over multiple time steps, and that can always be done. In fact, there are a lot of distributed algorithms that have been used for optimal power flow at the transmission level, and bulk grid level is sorry, I see the first comment, why speed is high. So in fact, at the bulk grid level, you have the mesh network, right? So you can work with it. So distributed algorithms work very well with the mesh network. The point I wanted to highlight here is that the algorithm that we have developed, which makes it possible for us to get faster convergence with fewer number of macro iteration, requires the network to be radial. If it is not radial, then we can go back to the original algorithms that are out there for distributed optimization and use them. The drawback is going to be that it will take a lot of macro iteration for us to converge, but that is still there. And we haven't looked into how we can speed up the mesh network optimization yet, because we're working on distribution and they are mostly radial. So yes, you can always do the distributed optimization with the mesh network. The challenge is going to be that how long it takes for you to converge. Hope that answered your question.
Thank you, ma'am. The next question is, what is the communication rate for solving distributed optimization? Like in case of the smart meters, we give the measurement in 2 to 5 minutes.
Sure. So that's true. So smart meters are a whole together different ballgame. What we are assuming at the level of distributed optimization that we are doing in this problem is basically you have a bunch of microgrid controllers, and these microgrid controllers can talk to each other as fast and as often they need to be. So there is a faster communication that is possible among these microgrid agents, and these microgrid agents can talk to their own devices at a faster speed as well. So the whole idea is basically this, that if you are working in a microgrid setup, let's say that this is a microgrid setup, you're working here, then you already have, you already have basically, this microgrid is already, let's say, set up. You have a microgrid controller already here, which has, bunch of control algorithms or control actions, control modules already implemented so that it can talk to its own generators, and it can basically optimize their operation for different kinds of things, for economic objective, for islanded setup. If that is already there, and if there is also these microgrids can also talk to each other in a reasonably fast time period, then you can work with network microgrid to actually achieve these solutions. If you have very slow communication that exists, for example 2 to 5 minutes, let's say it takes for every microgrid to send the decision to the other microgrid, then you're working at a very slow rate, and I don't think these methods will pan out that well in that case, because you will not get the system condition will change before you can really solve it. So that will be the challenge. So there are some inherent assumptions here.
Thank you, ma'am. Ma'am, next question is how to avoid the local optimal problems in the distributed optimization.
Yeah, so 2 things. So distributed optimization, if you solve if you have a convex problem and you do the distributed optimization in numerical optimization techniques, you use them to do that. The theory says that the optimal solution of the distributed optimization problem will be same as the optimal solution of the centralized optimization problem. So that is for the convex problems. The problem that we typically work at the power grid level are not convex. They are typical general nonlinear optimization problem. So even for the central model, we really cannot guarantee that we are getting non-local solutions. We are getting global optimal solution, because you are working with a nonlinear systems of equation. If you're going to solve an optimization on generated NLP, you can always get a local minima. That's always a possibility. Same thing happens at the distributed optimization as well. If you're trying to solve a nonlinear problem, here, for example, I was trying to solve a mixed integer linear programming problem, which is also nonlinear. So we did get local solution. The trick is not to get a local solution which is very bad. The trick is to get a local solution which is good enough, or good enough to centralized model. And that really relies on how your algorithms are working and what information you're exchanging and how you're designing your algorithm so that it's maximizing what you want to maximize with the local information available. And what we saw in this particular problem is that by exchanging those information that we were doing at the boundary, we were still able to get a good enough feel of the upstream and downstream network while locally optimizing, in this distributed setup, and get a solution which is close enough to the central solution that we are getting, assuming that the central solution is close enough to the global optimum that you'll be getting. So those are the tricks, really, that you design the problem properly and you design the communication and exchanges properly.
Thank you, ma'am. And there's another doubt, like if a microgrid is isolated, in that case, whether the communication channels will work.
Yeah, so that's a good question. There's a 2-part answer to that. So even if your microgrid is isolated, but let's say it could be isolated for different reasons, right? So one of the main reasons why it could be isolated is that you had an outage, and because of a grid outage, since the purpose of microgrid is to supply, resiliency to the local load, it was able to, it islanded itself so that it can provide resiliency service to its own load, right? If that is what happened, then microgrid is isolated. But if that extreme event or if that outage did not cause any problem to the communication network, then that microgrid might still be talking to the other to the central agent, or it can still talk to the other microgrid. So the communication network could be different from the microgrid network depending upon how you have set up your communication network. If it is set up on a power line communication, then it's quite possible that those power lines which are damaged, you can't communicate through them. But if it is different, if it's optical fiber or some sort of other communication network, then it's quite possible that it's still active while your power grid is not active and your microgrid is islanded.
Thank you, ma'am. There's one more question from Mr. Malik. So, if our problem is non-convex, then usually we utilize the heuristic optimization. But in case of convex, we utilize the analytical one. But you have mentioned you are utilizing non-convex. Sorry, you was utilizing the MILPs for non-convex problem.
Yeah, so modeling is really it's not a good categorization that if you have a non-convex problem, then it's only heuristic you can use. There are different ways of solving it. For example, optimal power flow problem in power systems are general non-convex problem, but there has been a lot of methods to relax them, convexify them, different kind of approximation techniques that have been used to get to a model which can still be formulated as a known mathematical model, right? So you can transform a nonlinear programming problem which is non-convex to a linear programming problem using different approximation. You can transform a nonlinear programming problem to a convex programming problem using different approximation. Likewise, in this case, what I really have is basically a mixed integer nonlinear programming problem. Now, mixed integer nonlinear programming problem is a very difficult problem to solve. So what I do is that I basically relax certain constraints to get to a mixed integer linear programming problem. Now, mixed integer linear programming problem has good solvers out there, which do not use, they still use some sort of heuristic, but they are more well-defined heuristic than a general meta-heuristic algorithm that you might be using. So there might still be advantage in you transforming your problem to a model, to a mathematical optimization model, which has a better techniques developed for it. For example, MILP has a much better techniques developed where different kind of methods can be used to solve this mixed integer linear programming problem to begin with, instead of using heuristic where there is really not a lot of guarantees which are out there, and there are challenges to scaling the problem as well. So what my recommendation will be that even if you have a difficult non-convex problem, try to get to it a form which is more well studied in mathematical optimization literature, so that you can come up with some solutions that you can have some certainty or some guarantees about.
Thank you, ma'am. And there's one more question from Mr. Suman. Sorry, Ms. Suman. Can the similar distributed optimization problem be formulated using a single objective, like for example, to meet loads only optimization problem or the multi-object problem? So we want to know what control strategy is adopted in the network microgrid control.
Right. So I think Gaurav, you cut off, but then let me try to answer this question. So the first question is basically why we use classical optimization technique instead of meta-heuristic, right? So there are several reasons for it. One of the main reasons is that the classical optimization techniques are very well studied, and that basically gives you more certainty and more surety on what results you are getting and how close to optimal that result is. So the optimality is very well studied. That's one reason. Then it's not just the optimality, right? When you try to solve any power systems related optimization problem, you have to think about the operational feasibility or the constraint violation. That's very crucial, because if your constraints are getting violated, then you will have different kind of operational constraints, operational challenges which you don't want to see in the power system. So you also want a guarantee on the feasibility of the problem. So what these mathematical or classical optimization techniques do is that they have some better way of quantifying the optimality and the feasibility of the solution that you're getting. That's where the meta-heuristic algorithms lack, because they do not provide you those kind of guarantees. Now, other challenge that we have noticed is also that meta-heuristic algorithms are not that efficient as well. So we try to solve, the same restoration problem that I have been showing, and I try to solve it for close to 1100 or some 1100 node feeder with close to 200 switches or something like that. And there were a bunch of integer variables and a lot of, continuous variable. And we formulated an MILP, and that MILP solves within 2 minutes. And the the point is really to approximate your model in a good enough way so that you do not end up, approximating something very crucial that you want to study. And that's what we did. So we approximated the model in a way that we can still take the main points that we want for the system to intact, that we do not end up, approximating the crucial details, but we can still get a reduced order model, which is MILP, that can be solved. Now, this can be solved within 2 minutes. We tried to implement different kind of meta heuristic, including genetic algorithm, PSO, and other things. They were iterating forever. It didn't converge. The challenge, meta heuristic work, but the challenge is that you have to tweak that algorithm a lot for different types of problem and different same problem for different systems, and that is the challenging part. And these classical optimization techniques are more well defined, even when you want to translate it from one system to other system, or you want to solve some general problem of the same problem class and those things, and that also makes them very attractive. Now, coming to your second question is what control strategy is adopted for network microgrid? We have been using mathematical classical optimization technique for all our problem solution, and for the reasons that I just stated. Even for the network microgrid control for restoration, we are using, of course, these classical optimization techniques where the 2 layers are solving 2 layers of MILP problem. The LP relaxation that we are getting is very good for the distribution system. As I said, system-specific approximations are always preferred over generalized approximation. So the approximation that we look into this distribution system, it encapsulates the crucial details very well. Now, if you think about general control strategy where we want to study very fast control, even there these classical control strategies or classical optimal control strategies will be preferred, because you can have more guarantees on what kind of solutions you are going to get and what solution is good versus what solution is bad. Okay. Are there any other questions? Okay, so yeah, I can hear you. Well, yeah. Hello?
क्रैश कर रहा है, तुम लोग कंटिन्यू करो.
Okay, so if you all can hear me, I can read the question actually. So there is one question: why the tie line switches have not? Hello?
Hello.
Yeah.
Can you hear me?
Yeah, I can hear you now.
Yeah, thank you. We have two more questions.
Yeah, so right. Go ahead.
So Mr. Kesan wants to know why the talent switches have not been considered while solving the problem. Is it something related to the mass description that have come due to the usage?
Yeah, so just to clarify, we are using the tie line switches in the problem formulation because they are crucial to use. You really cannot do restoration without tie line switches and sectionalizing switches. So we are using all sorts of switches in the network. The radial structure was mainly when we were discussing the distributed coordination problem before, but then for this particular problem, when we are working with the network, the 2-stage decomposition help us handle it. So in stage 1, you are finding out the optimal control for both tie line as well as sectionalizing switches to come up with a topology which is good, and then you go to the second stage on that topology to figure out what should be the optimal action within each area. So we are incorporating tie line switches and sectionalizing switches for the restoration, both problems.
Thank you, ma'am. Now our last question is from the Mr. Satish. So he's asking if he's right in case of bulk transmission system, dynamics are slow in compared to the localized microgrid with high inverter based generation. So he's asking how this couple with the microgrid control operations.
Okay. So let me try to separate this problem. So you're right, microgrid controller dynamics are much faster, but they are more crucial when these microgrids are islanded. So when I'm talking about bulk grid services, I'm assuming that these microgrids are grid connected, because if they're not grid connected, then they cannot provide any bulk grid service. Now, if they are grid connected, then actually all the dynamics within the system is really dominated by the bulk grid, more or less, right? So because what really happens is that your substation or your distribution substation becomes the voltage source, and really microgrid behave like more of a grid following kind of setup than really any kind of grid forming or the fast dynamic setup. So the point, the main point is that if you are using microgrids to provide bulk grid services, then they are grid connected, and if they are grid connected, they are operating more on the on economic operation mode than actually islanded and dynamic operation mode. So that really solves this problem. But if you ask me that will it solve it forever, this is a question that is still open, that if your distribution, let's say, has a very large number of inverter based resources, which are a lot of them are really grid forming, and you have connected transmission grid, what are the dynamic challenges that will emerge from there? I don't know answer to that. That is something that should be studied more.
Thank you, ma'am. So, and I just like to thank you for answering all those questions and for this great presentation. And it was a pleasure to have you with us. Now, with your permission, I would like to conclude this webinar. And I also like to thank all the participants for attending this webinar, and let them know that we have the next webinar at 5 p.m. today. So, ma'am, can we close this session?
Absolutely. Thank you, Gaurav, for hosting me. And thank you, everyone, for interesting questions. I hope I'm still audible. And yeah, do feel free to reach out to me if you have any other questions. My email, I think Gaurav should be able to share it with you. And it was fun talking here today. Thanks, everyone. Take care.
Yeah, have a good night, ma'am.
Yeah, thank you. Bye.